So this is problem 32 on the math subset test 1 for constructivism. So in this one, the question asks if vectors A and B are perpendicular. So we're given that A is perpendicular to B, and they're of this form, A1, A2, and B1, B2. We identify the vectors of the columns in this usual way. We want to show that this AX or AA times AB and AB. Sorry, we want to show that these two vectors are perpendicular for all values of theta. So we're given that A and B are originally perpendicular. We want to show that even though we multiply them by this vector, by this matrix A, the resultant product of these two vectors is also perpendicular. Okay, so we want to show this, okay, that AA and AB are orthogonal. So what does it mean for a vector to be orthogonal? So this is some of the background information that you'll need to know in order to be successful. Okay, so when it says that vectors A and B are orthogonal or perpendicular, then what that means really is that the dot product of the two functions is equal to 0. Okay, and for us, we notice that this is A1, A2, when we got it with B1, B2, what that looks like is A1, B1 plus A2, B2. That's equal to 0. Okay, so that's what we're given. We want to show that that's also true for this. So what we're really trying to show is that the dot product of this vector and this vector is equal to 0. Okay. A couple of things to note that this matrix is a square matrix. So A is a 2 by 2 matrix, and we're multiplying it by vectors A to the 2 by 1 and vector B, which is also a 2 by 1. And so the resulting column of A matches the dimension of the rows of both A and B. And so that means that the multiplication is well defined, and both situations are going to produce a 2 by 1 column vector. Okay, so just to verify that the dimensions are correct. Now we can continue this product by multiplying out each of these vectors with the corresponding matrices, and then we'll look at the dot product of the two. And if this condition is met, then we've shown that they're perpendicular. Okay? In other words, AA and AB are perpendicular. But let's find out. Okay, so we're going to multiply AA. So let's find out what this vector is. So we have cosine theta, and we have minus sine theta, and sine theta, and cosine theta. We have A1, A2. So matrix multiplication with a vector is kind of like the dot product of this row vector with this column vector. So you're going to multiply the cosine theta times A1, and then add to that the product of negative sine theta and A2. And that's going to be the top row. This is A1 cosine theta, line here, and then adding to it. But because it's a negative sign here, and this is positive, yeah, this is actually going to be minus A2 sine theta against row cosine sine theta. And I'm assuming that these elements are from a field where they're commutative, so I can write A2 in front. That's not always true, but I'm assuming in this situation that it is true. Okay, likewise, I have this row vector. I'm going to multiply it or use the dot product with these column vectors. So I have A1 sine theta, and I'm going to add to that A2 cosine theta. Okay, so that's what this vector looks like. It's this 2 by 1. Okay, there's the sum or difference in them, but it's still a 2 by 1. Okay, and then likewise, I'm going to compute A times B and see what I have there. So this is cosine theta minus sine theta and cosine theta, and multiply that by B1, B2. Okay, and in doing so, I get B1 cosine theta minus B2 sine theta. Okay, so that's coming from there. And then here I have B1 times sine theta, and then plus B2 times cosine theta. So here. So that's this, okay. And so now I have my AA and my AB. So now I need to dot these two vectors together and see if indeed I get that their dot product is equal to 0. If it is, then they are orthogonal and we have what we're trying to show. Okay, so AA dotted with AB, what do we have? We have this vector. So we have A1 cosine theta minus A2 sine theta. I'm going to multiply that by the first component of this vector, B1 cosine theta minus B2 sine theta. I'm going to multiply these two together. I have A1 cosine theta minus A2 sine theta times B1 cosine theta minus B2 sine theta. Okay, so obviously it's two binomials, so it can be a constant right there. Okay, so that's the first component. Okay, and then now I'm going to multiply the second components together. And because it's the dot product, I'm going to add the sum, the product of the two. So I have A1, I'll write that down here, A1, this is the first one here, A1 sine theta plus A2 cosine theta. Okay, so that's this term. I'm going to multiply that by this one, which is B1 sine theta plus B2 cosine theta. Okay. So now that I've done the dot product, okay, let's actually simplify things out and hopefully we'll get something that will cancel out. Okay, so I have A1 cosine theta times B1 cosine theta, and then I have A1 cosine theta times B2 minus B2 sine theta. Okay, so this is going to give me A1 B1 cosine squared theta, because cosine times cosine is cosine squared, and then A1 minus that, so A1 B2 cosine theta sine theta. Okay, so that's the product times this one. Okay, and then now I have minus B1 A2 sine theta cosine theta. And that's these two together. And then last but not least, that is minus B2 times the minus A2. That's going to be plus A2 B2. That's 5 squared theta looks like. Okay. A1 B2 B2 A1. Okay, yeah, it looks like so nothing cancels out here. Let's go ahead and add to it then. And now I'm going to multiply these two out. So I have A1 sine theta times B1 sine theta plus A1 B1 sine squared theta. That's the first one. And then it looks like a plus A1 B2 multiplying here. Sine theta cosine theta. Sine theta cosine theta. And then going here plus A2 B1 2B1 sine cosine theta, sine theta cosine theta, and then last but not least plus A2B2 times cosine theta, A2B2 cosine squared theta. Okay, so it just happens to line up nice and neat. That wasn't intentional, but it worked out really well. So I'm adding these together, and so I'm going to look for a common term. So I have A1, B1, A1, B1. So I can add those together, A1, B1, and then I have cosine squared theta plus sine squared theta, or what I've done is I factored out, they both have an A1, B1 term, so I factored that out of both of them. Okay. Looking here, I have an A1, B2, and A1, B2. Sine theta, cosine theta, sine theta, cosine theta. But I noticed that this is a minus A1, B2, and this is a plus A1. So those are opposite in sign, so they're actually going to thankfully cancel each other out. And then looking here, I have a B1, A2, a B1, A2 sign. And look, they're also in signs. So, so nice simplification happening. So those cancel each other out. And then I'm left with, looks like an A2, B2. Factor it out, A2, B2. And then I have a sine cosine squared. So sine squared theta plus cosine squared theta. Okay. Now, a well-known trigonometric relationship is the Pythagorean trigonometric relationship. And so I look here, both of these actually equal 1. Sine squared plus cosine squared or cosine squared plus sine squared. Either way, that's a Pythagorean identity for trig, and those both equal 1. So if I allow those to equal 1, then I have A1 B1 plus A2 B2. And lo and behold, if we go back up to what we were given, the dot product of A1 B1 plus that is just the dot product A1 B1 plus A2 B2. And that's equal to 0 because we were given that this is really nothing more than A dot B, which we know is equal to 0 since they were given to us that A and B were originally perpendicular or orthogonal. This does in fact equal 0. So what we've shown is A dotted with AB equals 0, which shows then that the corresponding vectors AA and AB are in fact orthogonal, perpendicular. Right? I hope that was helpful, and I'll see you in the next video.